Hello everyone, my name's Ollie Wing and I'm the Chief Research Officer at Fathom. In this presentation I'll be discussing a really exciting collaboration between Fathom, a flood risk modelling company in Bristol that I work for, Deltares, a flood modelling firm in the Netherlands, and AXA's catastrophe modelling team based in Paris. I'm merely the messenger of this excellent bit of science, leaning on the expertise of all of those listed here. So thanks to Hessel, Helene, Mark and Albrecht at Deltares, Remy, Ugo and Anna at AXA, and Andy and Chris at Fathom. So to start with, I'll give you the grand overview of the approach to build a European flood catastrophe model. A catastrophe model differs from other hazard or risk models by simulating long synthetic sets of plausible flood events. Without understanding spatial correlation, you cannot understand extreme losses. At the top then is a stochastic weather generator developed by AXA. This produces plausible weather patterns using a temporal reshuffling of historical data. Deltares' hydrological model consumes these 10,000 years of weather patterns and turns those into 10,000 years of stream flow. All the while, Fathom are producing return period flood maps to yield a catalogue of flood intensity probabilities. The 10,000 year time series is then used to sample from the hazard maps in space per event. So on to the weather generator. We developed a time resampling stochastic weather generator based on weather regimes and wet-dry alternation. It takes into account precipitation persistence and preserves historical observed statistics and extremes across Europe. 10,000 years of synthetic weather is therefore reproduced. This model essentially temporally reshuffles Era 5 reanalysis data. Entire days of weather are sampled from continent-wide and reconcatenated to produce new multi-day extremes. The reshuffling is based on three parameters: the clustering of historical data into weather regimes based on multiple variables that trigger precipitation at the European scale, a second clustering based only on precipitation patterns at a finer geographic scale, and dry and wet sequences of precipitation based on a historical distribution. With this approach, we can generate new sequences of precipitation accumulation. You can see here, for instance, the 200-year precipitation accumulation across 10 days. This plot, using the Rhine Basin as an example, shows how historical precipitation accumulations across 10 days, the red crosses, are extended to produce new and unseen 10-day extremes. Meanwhile, the spatial coherence of the flood events is implicitly retained. Deltares' distributed hydrological model WFlow then simulates the river flow response to these synthetic weather patterns. It does this at 2 kilometer resolution, so that the information content at higher resolutions is also preserved. There's a neat upscaling algorithm applied. Before the 10,000 year run though, as with all hydrological models, it needs to be calibrated. For this, Deltares used pedo transfer functions. Given the spatial scale of this model, we are not seeking a very heavy calibration to river gauges, but rather the approach was more like a sensitivity analysis to select sensible basin-wide pedo transfer parameters to maintain continent-wide spatial coherence. As such, the approach looked at the parameter which describes the relationship between horizontal and vertical conductivity of water in the subsurface. Optimal parameters for each basin were linked to existing constraint parameters to produce a coherent continental parameter set. Some of the Kling-Gupta efficiency scores for river gauges in particular countries are shown here. The QQ plots give a great example of the philosophy of this modelling approach. You can see that for this particular station, in those first two plots, that there's an obvious model bias. WFlow is over-predicting the flood response. But that rightmost plot shows the return period, calculated internally to model an observation separately of each flood event. You can see here that while those absolute discharges are biased, the relative frequencies of their exceedance are not. The reason why this is important will come in a second. Next up, we have Fathom's principal contribution to the project, the hydraulic modelling. We're producing multiple return period flood depth grids across the continent at 1 arcsecond resolution. River flows are estimated using the Zhao et al. 2021 regional flood frequency analysis, and pluvial intensity duration frequency relationships are estimated in a similar vein, using a machine learning approach to regionalize IDF curves computed from sub-daily rain gauges. Terrain data are drawn from LiDAR where we can find it, using Fathom, which is the Copernicus DSM, which some of you might also know as Tandem X, with forests and buildings removed, as the data set of last resort. The way we construct flood events is adopting the so-called cookie-cutter approach. This involves segmenting the hazard data from previously into subcatchments, and when an event, described by its relative frequency or return period in the 10,000-year hydrometric time series, occurs, we cut out the relevant flood map within that catchment and paste it into the event footprint. We repeat that for all impacted catchments and all events. Since we are matching return periods from the stochastic model to return periods in the hydraulic model, that's why spatial coherence and relative frequencies are so important. We've done some validation of these flood maps. This uses the calibrated historical hindcast simulated by WFlow, and from that we extract events for which we have reference data to benchmark the model. You can see here, for instance, the discharge simulation for a flood in Germany. We identify the return period of that event in that catchment, and then repeat to reconstruct the flood event. This graph is also a good illustration of the need for a 10,000-year stochastic model. You can see this event was unprecedented, around an 8,000-year return period, but the parameter estimates are really unstable based on only a few decades of flow data. With 10,000 years of flows, we can instead empirically understand the frequency of that event. Anyway, on to the validation. There are 10 events that we tested against, within which there are lots of subdomains and different types of data to test with. So I've just thrown a load of them onto the slide, though I don't actually expect you to interpret all that. For events which we had a water level observations for, on average across all events we get around a metre of water level errors. While that seems a lot, it's worth bearing in mind the considerable error in the benchmarks themselves. Separate studies show high watermark based water level measurements can be subject to half to 1 metre of error. Similarly, we evaluated flood extents, a less discriminatory test of the model, but it does tell us if we are broadly matching the local spatial patterns of historical floods. Note that errors in flood extent imagery are such that 2 independent classifications or images of the same flood often have around 75% similarity. We find, on average, flood extent similarity, accounting for both under and overprediction errors, of around 2/3. Ignoring overprediction, which can be unreliably tested by these benchmark datasets, 85% of wet pixels are captured by the models. These numbers are about in line with the expectations for a model of this scope and scale. And that's it. There's still a lot of work left to do in this project. All these components need bringing together, along with vulnerability functions, to generate the catastrophe model. Plus we have the small issue of creating climate-conditioned event sets, where we can explore the impact of projected climate change on European floods. If you have any questions, please do just talk to me or drop me an email. Thank you.